Well, hello everybody. My presentation is going to talk about compressed air energy storage, but specifically on the thermodynamics of the system. I made this presentation to let people not related with mechanical engineering know more or less, or like the basics of what happened with the energy in this kind of systems. Well, sorry. So the adiabatic case diagram. Case goes for compressed air energy storage, and the adiabatic here is more a name. Right now, there are a lot of people researching the adiabatic. I'm going to talk about it later. But the adiabatic in this case means that heat is added to the system. So I'm going to explain you quickly how does this system works, because we have been talking about the geomechanics and geophysics. First, power is input to the system. It can be from a renewable energy source, or it can be from an already running power plant. Then this powers up a compressor, compresses air. The air then is cooled down and stored in a cavern. After some time, when you need to produce energy from this, the cavern goes up to a combustion chamber. In the combustion chamber, heat is added, and then it is expanded in a turbine, which is connected to a generator and produces energy. In the case of the adiabatic system, after the compressor has a thermal energy, well, after the compressor and the heat exchanger that will be here, has a thermal energy storage unit. What is this for? The heat that you get after cooling it down here, it's stored there in order to use it before the expansion. So the air goes to the compressed, well, not to the compressor storage, but to the cavern, sorry, and then it's mixed again with the heat and goes to expansion. This way, no fuel is needed and no combustion chamber is needed. So now I'm going to explain you a little bit of each of the components in the chaos system. First of all, the power input. The power input, as I mentioned before, can be from a common fossil fuel power plant with steam turbine, gas turbine, nuclear power plant, any kind of power plant. Or it can be also brought from renewable energies. The compression process. There are three ways to do a compression process. One is isothermal, that is when the process is done with the pressure constant. The other is isentropic, which means that not heat is added and no heat is also escaping from the system, and it's a reversible system. And the common one, the polytropic, which is the mix between both. In this case, theoretically, an isothermal compression will need the least amount of work input, giving you the best efficiency. Although an isothermal compression is really complicated to achieve, there are some companies right now researching and trying to get a compressor which can be completely isothermal. For example, SustainX, a company from the US, has a patent of a compressor, a piston compressor that sprays water into the cylinder while compressing the air, and then the heat done created by the compression process goes to the water, and then it becomes vapor and is separated from the air. Although this is just a patent, nothing yet has been working, nothing yet is on production or in the industry. No isothermal compressor exists yet. But what many industrial processes do to approach an isothermal compression, it's a multi-stage compression. So with a multi-stage compression, you have one compressor, and after the first compressor or any compressor, you have a heat exchanger to cool down the air. You cool down the air, and go to the next compressor, and like that. In a paper published by Harman from the University of Stuttgart, he did analysis of a case system with a multi-stage compression, and he noted that using 2 stages is the best configuration in terms of efficiency and power input. It's even better than having more than 2 stages, because he says, well, every time you use a heat exchanger to cool or to heat up a fluid, in this case, there's some losses. So having multiple stages of compression can create a lot of losses. And having just one will make the air too hot, and then you will need to cool it down again, and the losses. But 2, for him, seems to be the best. Well, not seems to be. He proved in his methods and his calculations to be the best configuration. Before I go to the next slide, I'm just going to tell you that in this case, in the PV diagram of the 3 compression methods, the area under the curve of each is the work input to the system. So as you can see here, the isothermal one is the one with the smallest area, which means the smaller input work to the system. When you're running a chaos system and you don't have a constant power input, you have a variable power input for any reason, what will do that is that it will affect your your mass flow rate into the system. So a chaos system requires a big, really big and large mass flow rate. To do this, axial and centrifugal compressors are recommended. And actually, centrifugal compressors do not by nature have a very big compression rate. So axial compressors are the ones that fit best to this kind of system. Actually, axial compressors are the ones used in normal gas turbines. Let's now talk about the cavern. The cavern will be to store just cool air. Why? Because it has, well, first because it has a temperature limit. We cannot go higher than the limit because we can damage the cavern and maybe destroy it. And also it has a pressure limit. So the cavern for the K system is what rules many of the options or many of the variables that we can set or we can use. According to Zog, he said that the best temperature to use in a KS system would be for the air would be the natural temperature of the cavern, not just because of this temperature limit, but also because if you put air inside the cavern at the same temperature that the cavern usually has underground, less heat transfer will happen from the air to the surrounding of the caverns, thus giving you less losses in the system in general. Heat exchangers. Well, in a fluid-to-fluid heat exchanger or any heat exchanger which uses a fluid, it can be solid or liquid or gas, there's gonna be always 2 convection processes and 1 conduction process. For example, here simulating a double pipe heat exchanger. The conduction part of the heat exchanger will be always ruled by the thermal conductivity of the material, the surface area, and the temperature difference between both fluids, and the thickness of the material separating both fluids. This happens also if you use shell and tube heat exchangers or if you use a radiator. For convection, Convection is actually very similar, but there's a convection coefficient that to calculate these, usually there are tables containing this, but usually you need to do some experiments because the geometry, the fluid characteristics, the Reynolds number that's related with the speed of the fluid, all of these affect the convection coefficient. The surface area, which means at the end the size of the heat exchanger, and again the temperature difference between both, in this case both fluids. So if you have a big mass flow rate, a large mass flow rate, you will, and you want to have the same output temperature that by design you chose, you will need a bigger heat exchangers. No matter what heat exchanger you used, a high mass flow rate will require you to have a longer or a larger surface area, so a bigger heat exchanger. If everything else is set it up, like you already have the temperature of your other fluid, and you already have your output temperature that will go to the turbine. Anyway. Heat storage. Heat can be stored in two different ways. It can be stored sensible heat, which is when you heat up whatever material you want, its temperature rises, and then if you have it insulated, it can actually store that heat for quite some time. And latent heat. Latent heat happens when you heat a material. First, the temperature will rise for sure, and then it will get to, for example, if it's a liquid, it will get to a boiling phase. All the time that this material is boiling until it finishes and it's converted to completely superheated gas. All this time, the temperature was constant, and all the heat added during this time is the latent heat. So you can have some storage with these kind of materials, which usually called phase-changing materials. These materials are heated up, they get into boiling or melting, whichever you are searching for, at a constant temperature, and then you store it in a very good insulated tank or whatever insulated container. And then when you want the heat back, you can get it at the same temperature you use, well, not at the same, but at a constant temperature all the time this material is changing its phase. So in the case of latent heat storage, what you will look for is a material with a big latent heat, so that it can actually transfer you more heat during the change of phases. In the case of sensible heat, what I'm showing you here is one of the tanks used in Solana, that is a parabolic solar power plant in the US. This power plant works with the sun hits these devices and they heat up a special oil. Then the oil is used to heat molten salts that are in these tanks. So these molten salts can store a lot of sensible heat. And then they use these molten salts here to run the plant during the night or whatever other process they need when the sun is not actually available. So this is very similar to what it could be used in a case system. Okay, the expansion. Expansion happens in the turbine. Basically, a turbine, if you give it a specific amount of mass flow rate and energy contained in that mass, which is called enthalpy, it will, for a fixed turbine, if you give it a bigger mass flow rate and a bigger input enthalpy, it will give you the most work output. Of course, there's a limit. This enthalpy, it's made from the temperature of the fluid and its pressure. And the turbines have a limit. The turbines cannot stand certain pressures or certain temperatures. That's why in recent years there's been a lot of research, and well, since 40 years ago there's been a lot of research about better materials to stand high temperatures, to not get corrosion, etc. In today's steam turbine power plants, they use more than one. They usually use more than one steam turbine. Steam turbine, because like shown here, because this has a fixed enthalpy change, so they can put high pressure vapor here, expand it, then use a lower pressure or a medium pressure turbine, and then the next and the next. This way they can take advantage of the different configurations that you can get that you can give to a turbine when you are actually building the turbine. And when in power plants, usually there's a lot of load variation. So steam turbines, which are going to be similar to what we would use for a case. You have the valves at the beginning and at the end of the turbine to control the power output and the speed that will actually give you the power output from the generator. So if your load decreases here and you start gaining speed at the turbines, you have a flow control valve here and a back pressure valve here, which can adapt to the load in order to keep the frequency working as you need it for your grid. And well, one thing that I forgot to mention here is when you have a multi-stage compression system and you want to have the best efficiency and power at the lowest power input, the compression ratio of the first compressor and the next compressor, if it's the same, it will be better for the whole system. And in the case of the cavern here, when you are expanding the air inside the cavern, you're not expanding. When you're expanding the air in the turbines, the air inside the cavern will lose some mass, and the air will tend to occupy all the volume of the cavern. So there's going to be an expansion. This expansion will reduce the temperature of the air inside the cavern. And what's good from actually this type of cavern, salt caverns, is that heat, the temperature difference that you will have here, and the heat on the surroundings will come into the cavern and will help gaining some energy and compensating the energy loss that you're getting for the internal expansion that happens inside the cavern while you produce energy without filling the cavern at the same time. And this is all. Thank you very much. Do you have any questions?
I have a question from the web here.
Right.
Jorge, you mentioned that 2 stages of compression are best.
Yeah.
To one of your...
To Harman, yeah. Which I don't have here, but yeah, it's Harman.
No problem. Can you specify what pressure ratio this was
okay, according to...
from?
Sorry?
Can you specify what pressure ratio this referred to, and would it be... I'm sorry, give me the microphone, I should... Okay, we have a question from the web here for Jorge. You mentioned in your presentation that 2 stages are best, according to one of your authors there. Can you specify what pressure ratio this was determined for?
Okay, I don't have the exact pressure ratio that they use in this paper, but what I can tell you, it's in the book from Sengel, Thermodynamics and Engineering Approach, he mentions that if you have the same pressure ratio in both stages, it's the best to get the best efficiency for the system. But I don't really know what ratio did Harman use, but I have the paper there.
Okay, well, you could certainly forward it to this
yeah, for
gentleman
sure.
who's one of our partners here in the research project. Did you have any insight into why the author said 2 stages was best as opposed to 3 or 4?
He did the simulations and...
Okay, simulations.
Yeah, and when you have more than 2, you have more losses in the heat transfer. This is not just the... He didn't talk just about the compression, but the whole case efficiency.
The whole system efficiency.
Yeah, the whole system efficiency. So when you have multiple stages of cooling during compression, there are losses and losses and losses, which he says makes just the 2 stages system better than the others and better than the first one, better than just the first, better than just one compression, because if you, for example, store the air from just one compression stage, it will be very hot, and this heat will be lost. Imagine if you don't need to cool it down, you store it. This heat will be lost in the storage, from the storage. Yeah. So that's how he discarded the 1 stage and the multiple stages, because every time you cool it in a heat exchanger, you have some losses.
Sure. Okay, this conclusion apparently was for diabatic, CAES.
Yes.
Do you have any insight as to whether this would be the same for adiabatic?
Okay, in adiabatic, first of all, if you have like a perfect insulated system, and the worked input to the system cannot be more. Well, sorry, the work output to the system cannot be more than the work input. So you can store energy, like a battery, like a perfect battery, let's say. The energy you put, the energy you use. But in this case, the mass flow rate of an adiabatic system, when you produce, when you're generating power at the end, would be bigger, because without the combustion, your mass flow rate needs to be bigger to have the same power output that you were planning with that combustion one. Like all the ones currently in use combustion. So you need to consider, if it's an adiabatic, to consider a way bigger mass flow rate to compensate that. And one point that I didn't mention is in the adiabatic, when you have a heat storage, imagine you can perfectly insulate it and keep the storage there. The problem is when you want the heat back. The heat is there, but if you use a PCM material, a phase changing material, they cannot release the heat as fast as you want. There's also some papers that talk about theoretical improvements of adding some superconductors to the PCM material, etc. So that's a so far limitation of the case or advanced adiabatic. And I don't know if that clears their question.
Well, he did say here, these are not easy questions, and I would like to hear Jorge's thoughts on how round-trip efficiency should be calculated in a diabatic.
Diabatic.
Yes, in a diabatic CAES system.
Well, the way they use in the current plants in Henterf and...
Yeah, those are both diabatic. I'm not sure he actually meant diabatic or adiabatic, but in any case, let me rephrase let me go back and talk about your work in general. Part of your work product here is going to be addressing full cycle efficiency with different assumptions.
Yes.
Yes, okay.
Yeah,
so in a sense then, you're going to answer his questions as part of this research
Yeah,
project.
I didn't talk about my current research that I don't have results yet, but yes, I'm gonna simulate all these differences and different input ratios, adiabatic, different efficiencies in your storage, all the energy related things to the case and adiabatic case. And also we're gonna focus a little bit on how to operate the whole system for ancillary services. What's the difference? What the difference would be when you want it just for storage or as a clean energy, as a constant clean energy source, and compared it to a system just for making better cost for ancillary services, etc. Yeah, that's gonna be that's what my research is about.
It's all about, right. Any other questions from the audience? Okay. Thank you.
Thank you.